In March 1979, Voyager 1 glided toward Jupiter. Its cameras locked onto a swirling red oval astronomers had watched through telescopes for more than 300 years. But nothing, absolutely nothing, could have prepared scientists for what they were about to learn about this mysterious crimson mark drifting in Jupiter's atmosphere. The Great Red Spot wasn't just a storm. It was a planet-swallowing hurricane, so enormous that you could drop Earth into it twice and still have room left over. As Voyager's instruments stared into this cosmic vortex, they detected winds screaming at 400 miles per hour, fast enough to encircle our planet in just 6 hours. Its deep red color came from phosphorus compounds pulled up from Jupiter's depths, like the planet was bleeding its own atmosphere. But the biggest shock wasn't the size or speed, it was the age. While hurricanes on Earth burn out in days or weeks, this Jovian beast had been raging for centuries, refusing to slow down. Imagine a spinning top that simply never stops, powered by Jupiter's heat and rapid rotation. The storm turned counterclockwise, completing a full rotation every 6 Earth days, like a massive cosmic gear grinding inside Jupiter's atmospheric engine. Voyager's close-up images revealed details no telescope had ever seen. Smaller storms swirling around its edges like tiny cosmic predators circling a whale, sometimes even being absorbed. The storm's eye stretched 12,000 miles across, wide enough to swallow our moon. Temperature readings showed something even stranger. The storm's center was actually colder than the surrounding atmosphere, forming a high-pressure mountain floating in Jupiter's sky. But the biggest mind-bending discovery was still ahead.
Scientists realized the Great Red Spot was shrinking. Old drawings and observations showed it had been nearly twice as large only a century earlier. This cosmic hurricane was slowly dying, though it would likely survive for generations before fading away into Jupiter's churning atmosphere. And then came the revelation that changed everything. Just as Voyager finished observing Jupiter's storms, it turned its cameras toward the moons and captured something that made every scientist on Earth question the laws of physics. Jupiter's moon Io was erupting. Navigation engineer Linda Morabito noticed a strange, crescent-shaped plume rising 300 miles above Io's surface. At first, Mission Control thought it was a glitch or a background star, but as more images arrived, the truth became undeniable. Io was the most volcanically active world in the entire solar system. 8 eruptions were visible in that very first flyby. Explosions so powerful they blasted sulfur and sulfur dioxide hundreds of miles into space. These weren't gentle lava flows like those in Hawaii. These were planet-shaking detonations, strong enough to launch material off Io entirely and into orbit around Jupiter. Imagine standing on a world where the ground trembles constantly and mountains erupt with the force of nuclear weapons. Io's plumes formed umbrella-shaped clouds, spreading hundreds of miles before falling back as alien snow. Some eruptions reached 3,000 degrees Fahrenheit, hot enough to melt copper instantly. The surface changed so rapidly that features seen by Voyager 1 vanished by the time Voyager 2 arrived just 4 months later. The cause? Jupiter's gravity. Io was being squeezed and stretched like a cosmic stress ball by Jupiter and the neighboring moons Europa and Ganymede. This constant tidal flexing melted Io from the inside out, turning it into a world-sized volcanic engine. But while Io was exploding with fire, its neighbor Europa hid a secret just as extraordinary. From the Voyager view, Europa looked calm. A bright, icy moon with a surface smooth as polished glass. But the cracks etched across that icy shell told a different story. They formed organized patterns, like a shattered eggshell that had frozen mid-break. Scientists realized what they were seeing. Europa's thick ice wasn't solid ground. It was the frozen lid of a global ocean. Beneath 10 to 15 miles of ice, lay an ocean containing twice as much water as all of Earth's oceans combined. Tidal heating, the same force powering Io's volcanoes, kept this ocean liquid. The ice shell was constantly shifting, cracking, and refreezing, forming ridges and valleys that spread across the moon's entire surface. In some regions, the ice had split apart and refrozen, creating features that looked like frozen rivers. Europa was a cosmic egg. Crack it open, and instead of yolk, you'd find an ocean deeper than any trench on Earth. A dark, cold world untouched by sunlight, but still full of water, the key ingredient for life. For the first time, scientists began to seriously wonder, could something be alive in Europa's hidden sea?
The implications were enormous. If Europa truly held a global ocean, it meant that habitable environments could exist far out in the frozen outskirts of the solar system, well beyond the sun's warmth. Life might not need sunshine or comfortable temperatures after all. It might thrive in the cold, pitch-black depths of alien oceans, feeding on chemical energy instead of photosynthesis. Voyager's discovery instantly transformed Europa from a simple ice-covered moon into one of the most compelling worlds we've ever found. Its smooth young surface hinted that the ocean below was actively interacting with the ice above, cycling chemicals, nutrients, and heat between the two layers. That meant Europa's ocean wasn't just a dark basin of water sealed away for eternity. It was a living, dynamic environment capable of supporting complex chemistry. Until then, the search for life beyond Earth had always centered on planets in the habitable zone, where liquid water could flow on the surface. But Europa shattered that idea. Habitable worlds might be hiding in places no one ever expected, trapped beneath ice, orbiting giant planets hundreds of millions of miles from the sun. As Voyager left Jupiter behind and sailed towards Saturn, scientists knew they had stumbled upon something extraordinary, an entire hidden ocean world beneath a deceptively simple sheet of ice. But Saturn was waiting for even bigger surprises, and it all started with its rings. When Voyager 1 approached Saturn in November 1980, astronomers believed they understood the rings fairly well. Seen through telescopes, Saturn appeared to have just a few broad rings separated by dark gaps, like grooves on a cosmic vinyl record. But Voyager's close-up images shattered that assumption completely. The rings weren't solid bands at all. They were made of billions of individual pieces of ice and rock, each following its own orbit around the planet. Some pieces were the size of snowflakes, others were as big as houses. Together they formed a vast, swirling cloud, a shimmering storm of orbiting debris arranged in a gravitational dance that had been unfolding for millions of years.
From Earth, the rings looked simple. Up close, they split into thousands of ringlets, each with its own speed, thickness, and structure. The entire system resembled a cosmic photograph etched with grooves too fine to see from afar. Tiny moons acted as shepherds, sweeping ring particles into narrow paths and sculpting the edges. And despite their enormous width, stretching 170,000 miles, nearly half the distance from Earth to the moon, the rings were shockingly thin, only about 30 feet thick on average. If you scaled a sheet of paper up to the size of a football field, it would be thicker than Saturn's rings. In sunlight, the icy particles glittered like crushed diamonds. They weren't grimy chunks of rock. They were almost entirely pure water ice, likely formed when comets or small moons were torn apart by Saturn's immense gravity. Larger pieces tumbled slowly as they orbited, creating a gentle, never-ending cosmic snowfall. But the rings saved their strangest secrets for last. Voyager discovered structures that seemed to ignore the laws of physics. Some ringlets twisted together like braided ropes. Others displayed dark spokes, ghostly shadows drifting across the rings with no obvious source. These spokes would appear and vanish unpredictably, lifted above the ring plane by electromagnetic forces charging tiny dust particles. Saturn's gravity wasn't acting alone. Its magnetic field stirred the particles too, creating waves that rippled through the rings like vibrations on a drum. Small embedded moons carved out gaps and maintained sharp edges through gravitational shepherding, while distant moons created spiral density waves, frozen patterns resembling sonic booms in space. Far from being a static structure, Saturn's rings were alive with activity. Particles collided, clumped together, and shattered apart again, revealing a constantly evolving system. Scientists realized they were witnessing the ongoing birth and destruction of ring particles, a cycle that had shaped Saturn's rings for billions of years. Voyager's discoveries completely rewrote our understanding of how ring systems form and evolve, giving us the tools to study similar structures around planets light years away.
Hidden among Saturn's dozens of moons was a world so strange that it would completely rewrite what scientists thought they knew about planetary atmospheres. Out of Saturn's 62 known moons, one had always stood apart, even before Voyager arrived: Titan, Saturn's largest moon. Wrapped in a thick orange haze that concealed its entire surface, Titan looked like no other moon in the solar system. When Voyager 1 finally flew past Titan in November 1980, it revealed something astonishing. Titan's atmosphere wasn't just substantial, it was denser than Earth's. The pressure was 1.5 times higher than what we feel at sea level, making Titan the only moon where a human could walk around without a pressure suit. You'd still need oxygen and heavy insulation against the brutal cold, but the atmosphere itself was strong enough to support you. This orange shroud rose hundreds of miles above the surface, giving Titan an almost Earth-like glow from space. But this wasn't an atmosphere of nitrogen and oxygen like ours. Titan's air was 95% nitrogen mixed with methane that sunlight constantly broke apart. These fragments recombined into larger organic molecules, drifting down to the surface like cosmic snow and tinting the moon in shades of orange and brown. Shockingly, Titan also had weather, real dynamic weather that mirrored Earth's in eerie ways. Clouds formed and disappeared, winds circled the globe, and Titan experienced seasons as it orbited Saturn. But instead of water, methane evaporated, condensed, and fell as rain. Methane carved river channels, filled basins, and pooled into vast polar lakes, making Titan the only other world in the solar system with stable liquid on its surface. The atmosphere was so dense and gravity so low, just 14% of Earth's, that if a human could tolerate the cold, they could literally fly with wings strapped to their arms. Titan was a world where people could soar through orange skies above seas of liquid methane. Voyager's infrared sensors detected temperature variations across Titan that hinted at hidden landscapes beneath the smog. Warm equatorial regions likely covered in massive dune fields of organic sand, and colder polar zones marked by methane and ethane lakes. Titan was a natural chemistry laboratory. Complex organic molecules formed in the atmosphere, fell to the ground, and accumulated over millions of years, offering scientists clues about how life may have begun on early Earth. Titan's thick atmosphere shielded the surface from radiation and impacts, preserving this chemistry for geological ages. It was a time capsule, storing conditions that may resemble Earth before life altered our own atmosphere. But while Titan concealed its secrets beneath a veil of haze, another Saturnian moon was preparing to reveal one of the greatest surprises in the entire solar system. As Voyager 2 approached Saturn in August 1981, most of the mission's attention focused on the planet's rings and mysterious Titan. Yet the real breakthrough would come from a tiny, icy moon named Enceladus. At first glance, Enceladus seemed unremarkable. A small, bright sphere barely 300 miles across, covered in pristine ice that reflected sunlight so strongly it almost glowed. It looked like a frozen snowball drifting in the dark. But below its innocent exterior, Enceladus was one of the most geologically active worlds ever discovered. Voyager's images revealed almost no impact craters, meaning the surface was constantly being renewed. The southern hemisphere displayed ridges, valleys, and smooth fields of ice, terrain far too young for a moon this old. Something was reshaping Enceladus from within. Then,
Voyager made a discovery that stunned mission scientists. Near the South Pole, massive plumes of water vapor and ice particles were erupting into space, colossal geysers blasting material hundreds of miles above the moon's surface. These weren't gentle vents. They were explosive jets firing at over 800 miles per hour, fast enough for ice grains to escape Enceladus's gravity entirely. The plumes emerged from long parallel fractures scientists nicknamed tiger stripes. These cracks were mysteriously warmer than the surrounding ice, hinting that liquid water existed beneath the surface. Even more astonishing, the erupting material contained organic compounds and minerals that could only come from a subsurface ocean. Enceladus, like Europa, was hiding an entire global ocean, kept liquid by tidal heating from Saturn's gravity. The moon behaved like a cosmic pressure cooker. The ocean's water forced its way upward, escaping through fractures and erupting into space, where it instantly vaporized and froze, feeding Saturn's faint outer ring. This meant scientists wouldn't need to land on Enceladus to study its ocean. They could simply fly a spacecraft through the plumes and collect samples directly from the source. Temperature measurements confirmed that the tiger stripe region was far warmer than sunlight alone could explain. Internal heating, generated by tidal forces kneading the moon like dough, kept the ocean from freezing. The geysers weren't always steady. They pulsed, weakened, shut down, and restarted, implying a complex underground network of chambers and channels. Enceladus wasn't just geologically active, it was alive with motion, constantly venting the contents of its hidden ocean into space.
Enceladus was essentially the cosmic equivalent of Yellowstone's geysers, except its fountains weren't powered by volcanic heat, but by relentless tidal forces from Saturn. As Voyager left the Saturn system behind, scientists understood they had found one of the most promising locations in the entire solar system to search for life, a tiny frozen moon ejecting liquid water straight into space. But Voyager's next destination would unveil a world so bizarre it broke every expectation. 5 years after departing Saturn, Voyager 2 approached a planet unlike anything else orbiting our sun. Uranus hung in the void like a giant turquoise bowling ball, rotating completely on its side. Instead of spinning upright like every other planet, Uranus's poles pointed toward and away from the sun. This strange tilt produced the most extreme seasons imaginable. 42 years of continuous sunlight, followed by 42 years of total darkness at each pole. When Voyager 2 flew past Uranus in January 1986, it became the first and still the only spacecraft to visit this distant ice giant. Through Earth-based telescopes, Uranus had always appeared as little more than a dim blue-green dot. But Voyager's close-up photos revealed a world that looked eerily featureless, a smooth sphere with almost no clouds or storms visible. Its muted color came from methane in the atmosphere, which absorbed red light and reflected blue and green back into space. Unlike Jupiter and Saturn with their dramatic storms, Uranus seemed frozen in calm silence. The lack of activity puzzled scientists until they realized Voyager had arrived during the planet's quietest season, a time when one pole was aimed almost directly at the sun. Yet beneath that calm exterior hid one of the strangest magnetic fields in the solar system. Uranus's magnetic field wasn't aligned with its rotational axis like Earth's. Instead, it was tilted an astonishing 59 degrees, and even more bizarrely, it didn't pass through the planet's center. It appeared to originate somewhere in the mantle, producing a wildly lopsided magnetic environment that defied all existing theories of planetary magnetism.
This bizarre tilt suggested something catastrophic in Uranus's past, likely a collision with an Earth-sized body that knocked the planet sideways, scrambled its internal layers, and warped its magnetic field. It would have been one of the most violent events in the history of the solar system, powerful enough to reshape an entire planet. Voyager also discovered that Uranus had rings, though they were nothing like Saturn's brilliant icy bands. Uranus's rings were dark as charcoal, absorbing almost all the sunlight that hit them. These narrow, rope-like rings were held in place by tiny shepherd moons orbiting in the gaps, also discovered by Voyager. The dark particles were likely organic compounds that had been baked and blackened by radiation over millions of years. And just like the planet, Uranus's moons were full of surprises. Voyager found 10 new moons, bringing the total at the time to 15. Many of them showed geological activity that scientists never expected on such distant, frozen worlds. Some had ancient volcanism or tectonic reshaping, implying that Uranus's gravitational tug might generate enough heat to drive internal processes. But the strangest moon of all was Miranda. Miranda looked like it had been shattered and then pieced back together incorrectly. Its surface was a chaotic collage of mismatched terrains, smooth plains beside heavily cratered regions, enormous cliffs that dwarfed the Grand Canyon, and grooved landscapes that looked like cosmic corduroy. Miranda appeared as if several completely different worlds had been cut apart and glued together at random. A geological Frankenstein. Uranus's extreme tilt created the most unusual seasonal dynamics in the solar system. During the summer of each hemisphere, the sun never set for decades, while the opposite pole lay in unbroken darkness. The result was subtle but complex atmospheric behavior unlike anything seen elsewhere, though much of it remained hidden due to Uranus's distance from the sun. As Voyager 2 drifted away from this sideways world, it carried with it mysteries that would puzzle scientists for decades. Ahead lay its final planetary destination, a world deeper in the darkness where sunlight was 1,000 times weaker than on Earth. Voyager was heading toward Neptune.
Yet this seemingly frozen, distant world was about to reveal the most dynamic and violent atmosphere anywhere in the solar system. From afar, Neptune looked like a glowing blue marble, streaked with thin white clouds racing across its surface at unbelievable speeds. Unlike Uranus, which appeared calm and featureless, Neptune erupted with atmospheric energy despite receiving almost no sunlight. Its rich blue color came from methane in the atmosphere, but Neptune's hue was far deeper and more vibrant than Uranus's pale greenish tint. Voyager's instruments quickly detected something astonishing. Winds on Neptune were blowing at more than 1,500 miles per hour, faster than the speed of sound on Earth. These weren't gentle winds, they were supersonic hurricanes powerful enough to circle the entire planet in under 18 hours. The fastest winds in the solar system were raging on the coldest major planet, a contradiction that stunned atmospheric scientists. Dominating the planet's southern hemisphere was a colossal storm scientists named the Great Dark Spot. Similar to Jupiter's Great Red Spot, but proportionally even larger, this swirling hurricane could have swallowed Earth whole. Winds spiraled around a dark central vortex, rotating counterclockwise with terrifying force. Unlike Jupiter's centuries-old storm, Neptune's Great Dark Spot appeared to be young and constantly changing. But how could a world so far from the sun generate such extreme weather? Voyager discovered that Neptune radiated more than twice as much energy into space as it received from sunlight. The planet acted like a cosmic furnace, powered by heat left over from its own formation and by slow gravitational compression. This internal energy source fueled Neptune's hyperactive atmosphere despite its frigid location. The bright white clouds streaking across Neptune's sapphire blue surface were made of methane ice crystals forming high in the atmosphere, where temperatures plunged to minus 360 degrees Fahrenheit. These clouds traveled at different speeds than the layers beneath them, creating a multi-layered weather system with multiple jet streams stacked on top of one another. Some clouds formed and vanished within just a few hours, reshaping Neptune's appearance during Voyager's brief flyby. Neptune's magnetic field proved just as strange as Uranus's. It was tilted 47 degrees from the planet's rotational axis and shifted far off-center, almost half a planet's radius away from the core. This bizarre similarity to Uranus hinted that extreme magnetic tilts might be a defining trait of ice giants, forcing scientists to rethink how planetary magnetic fields are generated.
Then Voyager turned its attention to Neptune's largest moon, Triton, and immediately discovered something extraordinary. Triton orbited backwards, the only large moon in the solar system to do so. This retrograde orbit meant Triton wasn't born around Neptune, but was likely a captured dwarf planet similar to Pluto. Its capture would have been a violent event, destabilizing and destroying any earlier moons Neptune may have possessed.
Triton was anything but a frozen relic. Voyager first detected nitrogen geysers erupting from its surface, shooting dark material up to 5 miles high into the thin atmosphere. These plumes were likely driven by sunlight warming nitrogen ice beneath the surface, causing pressure to build until it burst through weak spots in Triton's crust. The discovery of active geology on such a distant, frigid world changed scientists' understanding of where geological processes could occur. If the faint sunlight at Neptune's distance could power eruptions on Triton, then geological activity might exist on many icy worlds once thought to be completely dead. As Voyager 2 departed Neptune and Triton, it had officially completed humanity's first, and so far only, grand tour of the outer planets. But the Voyager mission was far from over. More than 35 years after its launch, Voyager 1 was racing through interstellar space, well beyond Pluto's orbit, its instruments still functioning despite decades of radiation, cold, and cosmic dust. The most profound discovery of all was still waiting for it at the very edge of the solar system.
Mission scientists had long predicted that one day Voyager would reach the edge of the solar system, a mysterious boundary called the heliopause, where the sun's influence finally gives way to true interstellar space. But no one knew exactly where this boundary was, what it looked like, or how the spacecraft would experience it. The solar system isn't just planets drifting in empty darkness. It is embedded in a vast bubble shaped by the solar wind, a continuous stream of charged particles rushing outward from the sun. This invisible river of plasma pushes against the thin gas filling the space between stars, forming a protective shell around our entire planetary system. The heliopause is the place where the solar wind finally runs out of strength and is pushed back by the interstellar medium. As Voyager 1 traveled beyond 100 astronomical units, more than 100 times farther from the sun than Earth, its instruments began recording strange shifts in the space around it. Cosmic rays from deep space increased, while particles from the sun dwindled. Voyager was skinning the edge of a cosmic frontier no human-made object had ever reached. Then, in August 2012, the transition came. Within just a few days, the number of solar particles around Voyager plummeted, while galactic cosmic rays surged dramatically. In one moment, Voyager was still inside the sun's protective bubble. In the next, it had crossed into the space between stars. After 35 years of travel, humanity had taken its first step into interstellar space. The heliopause was nothing like the sharp border scientists once imagined. It behaved more like a blending zone where solar and interstellar forces tangled together. The magnetic field barely changed in strength across the boundary, a hint that interstellar space was more structured and orderly than anyone had expected. Voyager hadn't plunged into chaos. Instead, it found magnetic pathways and organized particle flows stretching across the galaxy. Interstellar space even sounded different. The plasma wave background shifted pitch, like stepping out of a busy highway into a quiet forest. Cosmic rays arrived more steadily, no longer shaped by the sun's storms. Voyager was sensing the local interstellar medium, the thin mixture of gas and dust filling the Milky Way, material foraged in supernovas, stellar winds, and ancient cosmic explosions. This was the raw substance from which new stars and planets would one day be born.
Voyager also revealed that our entire solar system is moving through the galaxy at 52,000 miles per hour, creating a bow wave in the interstellar medium, much like a boat cutting across a lake. Temperature measurements showed that interstellar space, though unimaginably thin, was actually far hotter than the space inside the heliosphere, around 80,000 degrees Fahrenheit. But with so few particles, a real thermometer would still read almost absolute zero. As Voyager 1 pushed deeper into interstellar space, it began writing the first chapter of humanity's exploration beyond the solar system, carrying its golden record outward into the cosmic ocean. But Voyager 2 was not far behind.
6 years after Voyager 1, in November 2018, Voyager 2 reached the same boundary, but its crossing could not have been more different. Instead of a clean transition, Voyager 2 encountered a chaotic, fluctuating frontier. It crossed the heliopause multiple times over months, as if the boundary were rippling and shifting like a flag in a cosmic wind. Sometimes the spacecraft was in interstellar space. Sometimes it slipped back into the solar wind. And occasionally it found itself in a strange in-between region where neither force dominated. The two Voyager crossings revealed that the heliosphere, the sun's protective bubble, wasn't a perfect sphere at all. It was lopsided, flexible, and constantly reshaped by both solar activity and the interstellar currents through which our solar system travels. Voyager 2's functioning plasma detector delivered the first direct measurements of interstellar plasma density. The results were clear. Interstellar space contained a thin but measurable gas, far denser than the solar wind. This material was compressed and heated by our solar system's motion, forming a bow shock ahead of the heliosphere. Both spacecraft also discovered something astonishing. The magnetic field in interstellar space was stronger and far more organized than anyone expected. Instead of chaos, Voyager found magnetic highways guiding cosmic rays for incredible distances across the galaxy. The cosmic ray environment outside the heliosphere was dramatically more intense, filled with high-energy particles from supernovas, black holes, and the violent hearts of distant stars. These particles held information about events spread across our corner of the Milky Way. Temperature readings revealed a strange contradiction. The plasma was blazing hot, but so diffuse that a human would instantly freeze. The few atoms present moved at enormous speeds, but there simply weren't enough of them to transmit heat. Together, the Voyagers showed that the interstellar medium was the galaxy's recycling bin, containing hydrogen and helium from the Big Bang, mixed with heavier elements produced inside long-dead stars. Everything needed to build new worlds drifted through this cosmic sea. The data pouring back to Earth began rewriting textbooks. The heliosphere wasn't a static bubble. It flexed and breathed as our solar system journeyed through different regions of the galaxy. Both spacecraft had become ambassadors of Earth, drifting through the darkness with humanity's first messages to any civilizations that might one day find them. Their nuclear generators would last perhaps another decade, sending home precious measurements from a region no spacecraft had ever explored. But before Voyager left the planets behind, it had survived one of the most dangerous environments in the solar system, Jupiter's deadly radiation belts. When Voyager 1 approached Jupiter, engineers knew they were sending the spacecraft into a region filled with lethal radiation. Jupiter's magnetic field, 20,000 times stronger than Earth's, trapped vast numbers of high-energy particles in invisible belts around the giant planet. These radiation belts could fry electronics in minutes and would kill an unprotected human almost instantly. Compared to Jupiter's radiation, Earth's Van Allen belts looked like a gentle summer shower beside a Category 5 hurricane. Charged particles spiraled along Jupiter's magnetic field lines at nearly the speed of light, creating a natural particle accelerator far more powerful than anything built on Earth.
The radiation was intense enough to damage Voyager's cameras even through their shielding. Scientists soon discovered that Io's violent volcanic eruptions were feeding Jupiter's radiation belts. Sulfur and oxygen blasted into space from Io became ionized and trapped by Jupiter's magnetic field, forming a donut-shaped cloud of charged particles that circled the planet. These ions were accelerated to tremendous energies, turning volcanic gases into relativistic bullets. Radiation levels varied dramatically across regions. Near Io's orbit, a human would receive a lethal dose in less than 1 second. Even at Europa's distance, radiation levels were thousands of times stronger than anything on Earth. Voyager's instruments detected radio emissions from Jupiter that were powerful enough to be picked up by amateur radio operators back on Earth, even before scientists understood their origin. Voyager's perilous journey through this radiation storm provided the first direct look at how planetary magnetic fields trap and accelerate charged particles. It revealed that Jupiter was home to a natural particle accelerator operating for billions of years, under conditions far more extreme than any laboratory could recreate. The other Jupiter moons experienced these effects differently. Io's atmosphere was constantly stripped away, while Europa's surface was bombarded so intensely that radiation broke apart water molecules, creating a thin oxygen atmosphere. Ganymede's magnetic field offered some protection, while Callisto orbited far enough away to escape the worst. Voyager's survival proved that a well-shielded spacecraft could endure even the most hostile radiation zones in the solar system, but it also revealed the immense danger awaiting any future human explorers. As Voyager escaped Jupiter's deadly magnetosphere, it carried with it priceless data about one of the most extreme environments in the solar system, and continued its journey toward Saturn, where new mysteries awaited.
When Voyager 1 caught its first glimpse of Saturn's North Pole in 1980, mission scientists thought the spacecraft was malfunctioning. The images seemed impossible, a perfectly shaped hexagon encircling Saturn's North Pole, a six-sided jet stream, sharper than any natural weather pattern ever observed, wrapped around the pole like an architect's blueprint carved into the clouds. Nothing like it had ever been seen on any planet. Weather systems in the solar system, on Earth, Jupiter, Mars, anywhere, were always circular, spiraling, chaotic. But Saturn's hexagon was something else entirely. It looked artificial, geometric, almost intentional. And it was massive. Spanning nearly 15,000 miles across, the hexagon was wide enough to hold 2 Earths side by side. Each of its 6 straight edges was longer than Earth's diameter, making it one of the largest and most coherent atmospheric structures ever discovered. This wasn't a simple storm either. The hexagon was formed by a roaring jet stream with winds exceeding 200 miles per hour, flowing in a perfect geometric loop without curving inward or outward. Fluid dynamics said this shouldn't be possible. Rotating fluids form circles, not polygons. Yet Saturn effortlessly broke the rules, carving a 6-sided masterpiece into its polar atmosphere. Scientists soon realized they were looking at a structure that had likely endured for decades or more. The hexagon wasn't drifting, fading, or distorting. It was stable, sharp-edged, and astonishingly precise, as persistent as Jupiter's Great Red Spot, but far more mathematically elegant. Later laboratory experiments provided clues. When circular jet streams and rotating fluids are disturbed by certain wave patterns, they can lock into polygonal shapes, triangles, squares, pentagons, hexagons, even octagons, depending on the wave's character. Saturn's hexagon was simply this phenomenon scaled up to a planetary level, a natural demonstration of the hidden geometry woven into fluid motion.
At the center of the hexagon spun a gigantic hurricane, complete with a well-defined eye. It was roughly the size of Earth and appeared to act as the anchor point for the surrounding hexagonal jet stream. Winds along the eye wall surged past 300 miles per hour, making it one of the fiercest storms in the solar system.
Temperature measurements revealed that the hexagon was actually colder than the surrounding atmosphere. The jet stream acted as a thermal barrier, preventing warm equatorial air from mixing with the polar region. This temperature contrast helped maintain the crisp boundaries of the hexagon, reinforcing its structure and enabling it to persist for geological timescales. The discovery of Saturn's hexagon proved that planetary atmospheres could produce structures of breathtaking mathematical precision. It was a mesmerizing blend of order and chaos, turbulent atmospheric convection organizing itself into one of the most perfect geometric shapes ever seen in nature. As Saturn's seasons shifted over its 29-year orbit, the hexagon changed subtly in color and brightness, but its six-sided form never wavered. It revealed a fundamental truth about rotating fluids in planetary atmospheres, that under the right conditions, nature can build shapes as precise as anything produced by engineering or mathematics. But while Saturn's hexagon showcased atmospheric order, the magnetic fields of the outer planets revealed something completely different: chaos, distortion, and extreme unpredictability. So when Voyager 2 flew past Uranus in 1986, scientists expected to find a magnetic field similar to Earth's, aligned with the planet's rotation and centered on the core. What they discovered instead was one of the strangest magnetic environments in the entire solar system, a magnetic field so distorted it looked as if a cosmic hammer had shattered Uranus's magnetic compass and reassembled it all wrong.
Uranus's magnetic field was unlike anything scientists had ever seen. Instead of aligning neatly with the planet's rotation axis, it was tilted a staggering 59 degrees, as if a cosmic hand had grabbed a bar magnet, twisted it sideways, and forced it back into the planet. Even stranger, the magnetic field didn't pass through Uranus's center. It was offset by nearly 1/3 of the planet's radius. The result was a wildly lopsided magnetic environment, unlike that of any other world in the solar system. Its magnetic strength varied dramatically depending on where Voyager measured it. In some regions, Uranus's magnetic field was stronger than Earth's. In others, it nearly vanished. Charged particles followed tangled, unpredictable trajectories rather than the clean, organized belts seen at Jupiter or Saturn. Voyager picked up particles spiraling in chaotic, corkscrew patterns that defied existing models of planetary magnetism. On Earth, the magnetic field comes from orderly electric currents in the molten iron core, producing a stable dipole, like a giant bar magnet. But Uranus behaved as though multiple smaller dynamos were scattered inside the planet, each producing its own magnetic field. The discovery suggested that something catastrophic in Uranus's distant past, likely the collision that knocked it onto its side, had scrambled its internal convection patterns and permanently distorted its magnetic structure. The consequences were spectacular. Uranus's auroras were nothing like Earth's graceful curtains of dancing light. Instead, they appeared as chaotic knots, spirals, and flickering patches that jumped unpredictably across the atmosphere, guided by the distorted magnetic field's twisted pathways. Temperature measurements revealed that Uranus's magnetosphere was surprisingly cold. Its broken, misaligned magnetic field couldn't efficiently trap or heat charged particles the way Jupiter and Saturn's powerful fields could. That made Uranus's magnetosphere not only asymmetric and chaotic, but also relatively quiet compared to the intense radiation environments of the larger gas giants. The magnetic data also hinted at something unexpected deep within Uranus: layered interiors. Instead of a fully mixed fluid like Jupiter or Saturn, Uranus seemed to contain partially separated layers of water, ammonia, and methane ices. These layers likely had different electrical properties, each contributing in varying degrees to Uranus's tangled magnetic field. A planetary interior more like a stratified cocktail than a well-stirred ocean.
As Voyager departed Uranus, it continued detecting bizarre magnetic signatures. The planet's magnetic tail, the long extension of its magnetosphere stretching away from the sun, was twisted into a rotating corkscrew, spiraling like a helical ribbon through space as the planet turned sideways on its axis. It was unlike anything seen anywhere else in the solar system. Uranus proved that planetary magnetic fields could be far more complex, chaotic, and unpredictable than scientists had imagined, windows into the violent processes that shaped the outer solar system. But the magnetic strangeness at Uranus was only a preview of what awaited at Neptune. When Voyager 2 photographed Neptune's Great Dark Spot in 1989, scientists believed they were seeing another long-lived storm, like Jupiter's ancient Great Red Spot. The swirling storm system was proportionally even larger than Jupiter's, easily capable of swallowing Earth. Yet 5 years later, when the Hubble Space Telescope examined Neptune, the Great Dark Spot had vanished without a trace. Such a dramatic disappearance baffled atmospheric scientists. Jupiter's Great Red Spot had persisted for centuries without fading, so how could Neptune's equally immense storm evaporate in under a decade? The answer lay in the fundamental difference between gas giants and ice giants. Neptune's atmosphere is far more dynamic and unstable than Jupiter's, driven primarily by an intense internal heat source rather than solar energy. This internal engine fuels rapid atmospheric turnover, allowing storms to appear and disappear on human timescales. Jupiter's thicker atmosphere and lower energy density create slower, more stable weather systems, allowing storms to linger for centuries. Neptune, by contrast, is a cosmic weather laboratory, a world where atmospheric features evolve, shift, and dissolve with astonishing speed.
The Great Dark Spot itself was an anticyclonic storm, with winds rotating opposite the planet's rotation. It wasn't just a storm, it was a colossal atmospheric engine born from the interplay of Neptune's fierce winds, intense heat flux, and frigid, fast-moving jet streams. These high-pressure systems were rare in planetary atmospheres. They required finely tuned conditions to form and survive, and when those conditions shifted even slightly, the storms collapsed and faded into the surrounding turbulence. Hubble's long-term monitoring revealed that Neptune regularly creates and destroys large dark spots. New storms would appear in fresh locations, grow to planetary scales, linger for months or years, and then vanish as atmospheric patterns changed. Neptune wasn't just home to storms, it was a storm factory, constantly producing and recycling colossal weather systems. The disappearance of the Great Dark Spot showed scientists that Neptune's atmosphere was far more active than its great distance from the Sun would suggest. Even though Neptune receives only 1/1000th of the sunlight that Earth does, it generates the most dynamic weather in the solar system, powered almost entirely by internal heat. Neptune radiates 2.5 times more energy than it receives from the Sun, fueling intense convection currents that churn the atmosphere and drive rapid weather shifts. This realization transformed scientists' understanding of the ice giants. Uranus and Neptune operate under a completely different set of atmospheric rules than Jupiter and Saturn. While Jupiter and Saturn possess long-lived, stable features that persist for centuries, the ice giants exhibit rapid, unpredictable evolution, capable of reshaping the entire planet within decades. Studying them was like watching weather systems evolve in real time, a level of variability unheard of on the larger gas giants. The fact that major atmospheric structures could appear and disappear within a human lifetime revolutionized planetary science. It suggested that many planets across the galaxy might have highly variable atmospheres, with dramatic changes occurring on human timescales rather than over geological ages. This made Neptune and Uranus some of the most dynamic and unpredictable worlds in the solar system. Temperature and wind measurements revealed that Neptune's atmospheric activity was driven by powerful convection currents carrying heat from deep within the planet up to the upper atmosphere. These convection cells formed, merged, and collapsed like colossal cosmic thunderstorms, capable of spawning massive vortex systems, including the Great Dark Spot itself.
Neptune's rapid atmospheric evolution also hinted at long-term seasonal effects. With each season lasting more than 40 Earth years, slow changes in solar illumination may influence atmospheric patterns, causing shifts that unfold over decades.
As the Great Dark Spot faded into memory, scientists were reminded that the outer planets were far from static. They were dynamic, living systems capable of dramatic transformation over surprisingly short periods. But while Neptune's storms came and went, the two Voyager spacecraft carried something built to endure for as long as the universe itself: humanity's message to the stars. Attached to each spacecraft was one of the most ambitious creations in human history: a golden phonographed record, containing sounds, images, and greetings from Earth, crafted to communicate with any alien intelligence that might one day discover the spacecraft. This cosmic time capsule was humanity's first introduction to the wider galaxy. The golden record held 115 images portraying life on Earth, diagrams of human anatomy, the structure of DNA, scientific symbols, landscapes, animals, plants, and photographs of people from cultures all around the world. It contained the sounds of Earth: whale songs, thunder, birds, a baby crying, a heartbeat, a kiss, and footsteps walking across the ground. Its musical selections spanned continents and centuries, from Bach and Beethoven to traditional folk music, forming a sonic tapestry of human civilization. Creating an interstellar message posed unprecedented challenges. How do you communicate humanity to beings who might think in ways we cannot imagine? The solution was to begin with universal truths: mathematics, physics, and fundamental constants, ideas any technological civilization would understand. These formed the foundation upon which the record built more complex information about life, Earth, and humanity. Even the cover of the golden record carried meaning. It contains symbolic instructions for how to play the record, encoded in mathematical diagrams meant to transcend language entirely. The instructions for playing the golden record were engraved directly onto its protective cover, depicted as diagrams that explained how to construct a stylus and determine the correct playback speed. These instructions used the hydrogen atom's fundamental spin transition as a universal time reference, a constant any advanced civilization capable of finding Voyager would certainly understand. The diagrams also showed the position of the Sun relative to 14 nearby pulsars, each marked by their distinct rotation frequency. Together, these pulsars formed a cosmic address, a stellar map that pointed unambiguously back to Earth. The record carried spoken greetings in 55 languages, ranging from ancient Sumerian to modern Mandarin. Each greeting offered a simple message of peace, humility, and hope, acknowledging that any beings who discovered Voyager would almost certainly possess technology far beyond our own. The sheer variety of languages highlighted humanity's cultural diversity while emphasizing our shared desire for communication and understanding. The hour and a half of music on the record told the emotional story of human civilization. Classical compositions revealed our mathematical grasp of harmony and rhythm, while folk music showcased cultural traditions that spanned continents and centuries. The selections reflected the full spectrum of human experience: joy, sorrow, longing, spirituality, offering any listeners a glimpse into the emotional pulse of our species. Scientific diagrams illustrated human reproduction, the structure of DNA, and the mathematical foundations of fundamental physical constants. These images attempted to convey what humans are as biological beings and how we intershape the universe. The record even depicted the trajectory of the Voyager spacecraft themselves, showing where they came from and how far they had traveled. But perhaps the most poignant part of the golden record was its portrayal of Earth as our fragile home. Images of the blue planet suspended in the darkness of space, along with photographs of oceans, forests, deserts, animals, and cities, offered a sweeping portrait of the only known cradle of life in the cosmos. Designed to last billions of years in interstellar space, the golden record may outlive humanity, Earth, and even the Sun itself. Encased in an aluminum cover protected from cosmic radiation and micrometeoroid impacts, it will drift through the galaxy long after our civilization has faded. Should an alien species ever find it, they would be holding a message from a vanished world, the echo of beings who once reached for the stars. As the two Voyager spacecraft carried their golden records into the vast darkness between stars, they embodied humanity's enduring hope that we are not alone. They were our message in a cosmic bottle, cast into an ocean whose shores we may never see. But meanwhile, closer to home, Voyager was uncovering magnetic mysteries around Jupiter that challenged every assumption about how small worlds could generate their own magnetic shields.
Among Jupiter's 4 largest moons, Ganymede immediately stood out. From the moment Voyager 1 detected its unusual properties, it became clear that this icy world, larger even than Mercury, possessed something no other moon in the solar system had: an internally generated magnetic field strong enough to carve out its own miniature magnetosphere inside Jupiter's deadly radiation belts. This discovery stunned planetary scientists. Moons weren't supposed to have magnetic fields. They were too small, too cold, too geologically quiet to sustain the molten, convecting cores that create planetary magnetism. Yet Voyager's instruments left no doubt. Ganymede was generating its own magnetic bubble, a pocket of safety within Jupiter's radiation storm. The implications were profound. Ganymede's magnetic field meant that the moon must possess a partially molten iron core, similar to Earth's, albeit on a smaller scale. Tidal heating from Jupiter's immense gravity likely kept part of Ganymede's core liquid, allowing electric currents to flow and power a dynamo. This magnetic shield dramatically improved Ganymede's potential habitability. While Europa and Io endured relentless radiation bombardment, Ganymede's magnetosphere deflected many of the high-energy particles, creating regions where complex chemistry could occur without being immediately destroyed. Voyager's measurements revealed just how effective this shield was. Even though its magnetic field was only about 1% the strength of Earth's, it was powerful enough to form distinct regions where Jovian radiation was excluded or rerouted, creating a miniature, moon-sized version of Earth's protective environment. The magnetic clues also revealed that Ganymede's interior was far more complex than anyone had imagined. Instead of being a simple mixture of rock and ice, Ganymede appeared to have multiple differentiated layers: an iron core, a rocky mantle, and several layers of ice that might contain subsurface oceans. This internal layering suggested vigorous geological activity early in Ganymede's history. Voyager also detected variations in Ganymede's magnetic field as the moon orbited Jupiter. The magnetic poles shifted slightly, and the field's strength changed with position, evidence that Ganymede's magnetic dynamo was influenced by Jupiter's tidal forces, linking internal geology with orbital mechanics in a complex dance unlike anything seen before.
Ganymede's magnetic field didn't just affect its interior, it transformed the moon's thin atmosphere in unexpected ways. Charged particles trapped within its miniature magnetosphere produced faint auroras shimmering over the poles. These weren't the bright curtains of light seen on Earth, but delicate ultraviolet glows detectable only with specialized instruments. Even so, they represented a historic first, the first auroras ever discovered on a moon. This revelation forced scientists to reconsider their assumptions. If Ganymede, a frozen moon, could generate its own magnetic field, perhaps other large moons in the solar system could as well. This opened new possibilities for finding magnetically protected pockets where complex chemistry and potentially even life might endure despite the brutal radiation belts surrounding giant planets. The discovery shattered the simplistic view of moons as geologically dead, inactive worlds. Ganymede proved that small bodies could hide molten interiors, magnetic dynamos, layered structures, and protective magnetospheres. They were more than planetary leftovers. They were dynamic, evolving worlds in their own right. But where Ganymede revealed internal complexity, another moon showed something far more shocking: a surface torn apart by ancient violence. When Voyager 2 flew past Uranus's small moon Miranda in January 1986, it revealed perhaps the strangest landscape in the entire solar system.
Only 300 miles across, Miranda looked as though it had been destroyed and then sloppily stitched back together by cosmic forces with no sense of order. Its surface was a chaotic mosaic that defied every rule of planetary geology. Miranda was divided into wildly different regions that seemed to belong on entirely separate worlds. Smooth, relatively young plains sat beside ancient terrain riddled with craters. Vast grooved regions, called corona, stretched across the moon in parallel ridges and valleys that extended for hundreds of miles. Enormous cliffs rose from the landscape as though parts of the crust had been lifted and flipped inside out. The moon resembled a jigsaw puzzle with mismatched pieces jammed together. The most dramatic feature was Verona Rupus, a cliff plunging an incredible 12 miles straight down, the tallest known cliff in the solar system. On Earth, such a fall would last only seconds, but on Miranda, with its weak gravity, it would take over 10 minutes to reach the bottom. A person could literally leap from its edge, take a short nap, and wake up before landing. Scientists were baffled. Miranda was far too small to retain heat from its formation, yet the surface displayed unmistakable signs of recent geological activity. The grooved regions looked stretched and twisted, as though enormous forces had pulled the moon's crust apart. The smooth plains hinted at resurfacing events that erased older features. One early theory proposed that Miranda was shattered by a colossal impact long ago. The explosion may have broken the moon into fragments that later reassembled under gravity, mixing layers and terrain types like a cosmic salvage job. This catastrophic breakup and reformation scenario could explain the bizarre patchwork surface. But a more convincing explanation soon emerged. Miranda's orbit placed it under intense tidal stresses from Uranus, amplified by orbital resonances with nearby moons. These gravitational interactions may have generated just enough internal heat to activate geological processes, stretching the crust, forming the coronae, and resurfacing large regions of the moon. The grooved terrains showed signs of extensional tectonics, where the surface had been pulled apart, forming parallel ridges and valleys. Tidal forces from Uranus likely created bulges and flexing across Miranda, kneading the moon like dough and forcing the crust to crack and reorganize over millions of years. Temperature readings revealed that Miranda was one of the coldest worlds ever explored, with surface temperatures around minus 300 degrees Fahrenheit. At those frigid extremes, water ice behaves like stone, struck enough to build giant cliffs, towering ridges, and the immense grooved provinces that define the moon's chaotic face. With so little solar heat, any geological activity had to be powered internally, primarily by tidal heating. Miranda was a frozen world reshaped by invisible gravitational hands, sculpted into one of the most violently disrupted landscapes in the entire solar system.
Miranda's wildly diverse terrain suggested not just one era of geological activity, but multiple episodes separated by long periods of dormancy. Different regions of the moon appeared to have awakened and shut down at different times, giving Miranda the appearance of a geological museum, a frozen exhibit displaying the fractured history of a world reshaped again and again. Miranda proved that even the smallest worlds in the solar system were capable of astonishing geological complexity. Size, it seemed, wasn't everything. With the right combination of orbital resonances and tidal heating, even a tiny moon could undergo dramatic transformations despite lacking the radioactive heat that drives geology on larger planets. But while Miranda's surface revealed the violent chaos of tidal sculpting, Saturn's rings showcased the opposite: order, precision, and gravitational harmony on a breathtaking scale. When Voyager 1 approached Saturn, scientists expected a clean, orderly ring system, thin bands separated by empty gaps. Instead, they found one of the most dynamic, intricate, and gravitationally choreographed structures in the solar system. Tiny moons acted as celestial shepherds, sculpting and guiding the movements of trillions of particles with nothing more than their gravitational pull.
Nowhere was this more dramatic than in the narrow F-ring shepherded by two small moons, Prometheus and Pandora, which orbited on either side like cosmic border collies herding a flock of icy grains. These shepherd moons kept the F-ring confined through a delicate gravitational dance. When particles drifted inward toward Prometheus, its gravity accelerated them, lifting them back into stable orbits. When particles wandered outward toward Pandora, that moon slowed them down, nudging them back into place. But this shepherding was anything but gentle. Voyager's images revealed the F-ring twisting and writhing with kinks, clumps, braids, and knots that shifted over just hours. Some parts appeared woven like rope, others bulged and twisted like strands of cosmic spaghetti pulled by invisible fingers. The ring was alive, reshaped moment by the gravitational pushes and pulls of its shepherd moons. Prometheus and Pandora weren't alone. Voyager discovered that many ring gaps were carved and maintained by tiny embedded moonlets. These miniature moons swept up particles along their orbits, clearing out gaps and maintaining razor-sharp edges in the surrounding ring material.
One striking example was the Encke gap, maintained by a small moon named Pan. Only about 20 miles across, Pan orbited inside the gap like a celestial snowplow, generating spiral waves that rippled through the ring system like a stone dropped into a cosmic pond. The ring particles themselves weren't passive. They responded to gravitational resonances, rhythmic tugs occurring when ring particles completed exact fractions of an orbit relative to a moon. These resonances created finely detailed patterns, sculpting arcs, waves, and edges with mathematical elegance. Scientists soon realized they were witnessing a cosmic ballet choreographed entirely by gravity. Every particle, every moonlet, every shepherd moon moved in a precise gravitational relationship that had been stable for millions of years. Each particle knew its place in the dance, guided by the subtle but powerful influence of Saturn's moons. Thermal measurements revealed that gravitational interactions did more than sculpt orbits. They could heat the rings. Regions near shepherd moons showed temperature variations caused by particle collisions and tidal friction, proving that even microscopic ice grains participated in the energetic dynamics of the rings. This discovery changed everything scientists thought they knew about ring systems. Saturn's rings weren't static relics. They were living, evolving structures, shaped moment by the gravitational interplay of moons and particles. Shepherd moons demonstrated that even tiny worlds could shape vast regions of space with precision and power. But beyond these stunning visual structures, Voyager was also capturing something even more mysterious and profound: the sound of space itself. As both Voyagers traveled through the solar system and out into the interstellar medium, their instruments picked up something that defied the popular belief that space is silent. The vacuum itself carried electromagnetic waves, plasma oscillations vibrating through the thin gas between the planets. These weren't sound waves, but they could be converted into audio, revealing an eerie cosmic symphony hidden within the void. When scientists played these recordings, they heard planets speaking in electric voices, whistles of charged particles spiraling along magnetic fields, roaring plasma waves, strange electronic choruses echoing through magnetospheres, rhythmic pulses from distant cosmic structures. Jupiter produced some of the loudest, most dramatic emissions, radio waves powerful enough to be detected by simple shortwave radios on Earth. Voyager recorded whistling tones from Jovian lightning and haunting chorus-like sounds generated by electrons dancing along Jupiter's magnetic field lines. It was the universe singing, a song no human ear was meant to hear,
yet one the Voyagers carried back to us from the depths of space.
Jupiter was effectively broadcasting its own radio station across the solar system, a roaring electric symphony of plasma waves and magnetic storms. Saturn's plasma waves told an entirely different story. They revealed the intricate interaction between the planet's rings and its magnetosphere. As charged particles spiraled through Saturn's magnetic field and collided with ring particles, they generated electromagnetic disturbances that rippled outward like cosmic thunder. Voyager recorded these interactions as bursts of crackling static punctuated by eerie musical tones, sounds so strange that scientists joked they seemed to come from the rings themselves. But the most haunting sounds emerged from interplanetary space, where the solar wind played its own cosmic symphony. As streams of charged particles from the sun crashed into planetary magnetospheres or interplanetary magnetic boundaries, they produced bow shocks that echoed through space as ghostly whistles and whooshing tones. These were the songs of the solar wind, the voice of the sun flowing past obstacles in its endless outward journey. Voyager's plasma wave instrument could detect frequencies from 10 Hz to 56 kHz, a range that spans human hearing once converted to audio. Scientists soon learned that different plasma waves carried their own distinct signatures. Electron-cyclotron waves chirped like birds. Ion acoustic waves rumbled like distant ocean surf. Chorus waves sounded like ethereal whistles drifting through the void. Each region of space had its own acoustic fingerprint, shaped by local plasma conditions. The most profound plasma wave discovery came when Voyager 1 crossed into interstellar space. The spacecraft detected a sudden, dramatic shift, like stepping from a noisy factory floor into a silent cathedral. The chaotic turbulence of the solar wind faded away, replaced by the steady, organized hum of the interstellar medium. For the first time in history, humanity heard the sound of interstellar space. Plasma waves weren't just eerie curiosities, they were powerful diagnostic tools. Their frequencies, amplitudes, and propagation patterns revealed plasma density, temperature, and magnetic field strength, information impossible to obtain through cameras or optical sensors. Voyager was using space itself as a musical instrument, plucking its electromagnetic strings to reveal the hidden physics of planetary magnetospheres. Plasma waves also unveiled processes invisible to the naked eye. Voyager detected waves produced by charged particles plunging into planetary atmospheres, creating electromagnetic signatures of auroras on worlds too distant to photograph directly. The spacecraft could hear auroras on planets where no camera could see them, expanding humanity's senses beyond visible light.
Some of the most mysterious plasma waves came from interactions between moons and the magnetic fields of their parent planets. Moons like Io and Europa, moving through Jupiter's magnetosphere, generated immense electric currents that produced distinctive radio emissions. These interactions formed a kind of magnetic handshake between moons and planet, a coupling mechanism previously unknown. As the Voyagers ventured farther, they collected an ever-growing archive of cosmic sounds, charting the electromagnetic heartbeat of the solar system and beyond. But plasma waves were only one part of the story. Voyager was crossing a cosmic frontier filled with invisible boundaries sculpted by the solar wind. Voyager, the cartographer of invisible worlds. Throughout their 45-year journey, the Voyager spacecraft acted as cosmic surveyors, mapping unseen boundaries created where the solar wind met obstacles in its path. These boundaries weren't visible in photographs. They revealed themselves through abrupt shifts in magnetic fields, particle densities, and plasma wave activity. The first major boundary each Voyager encountered was the bow shock at Jupiter. Here, the solar wind, rushing at over 100 million miles per hour, slammed into Jupiter's magnetic field and was forced to slow, bend, and compress. The result was a standing shockwave in space, akin to a sonic boom, but made of charged particles. Every giant planet produced similar structures.
Voyager found that the solar wind carved out distinct regions. The magnetosheath, a turbulent, chaotic zone between the bow shock and the magnetosphere, filled with superheated, compressed solar wind particles. The magnetosphere, a protected cavity where the planet's magnetic field dominated and the solar wind could not penetrate. These boundaries pulsed and flexed like living structures. When intense solar storms erupted, magnetospheres compressed dramatically, sometimes pushing boundaries inward by hundreds of thousands of miles. During quiet periods, magnetospheres expanded outward again. Voyager watched these cosmic lungs inhale and exhale in real time. Saturn's magnetosphere was especially sensitive. Its weaker magnetic field meant that powerful solar storms could compress it enough to temporarily expose some of Saturn's moons directly to the solar wind, a dramatic reminder that even enormous magnetic shields could be overwhelmed. But the most significant boundary discovery came in December 2004, when Voyager 1 encountered the termination shock, the point where the solar wind finally slowed from supersonic to subsonic speeds as it met the resistance of interstellar space. This wasn't a tidy, well-defined line like the bow shocks at planets. It was a messy, multi-layered region where the solar wind gradually transformed into a turbulent, slower flow. Voyager 1 crossed it multiple times as shock structures shifted back and forth, buffeted by solar activity, a cosmic ping-pong match of shock waves and magnetic pressure. Temperature measurements revealed that crossing these boundaries produced dramatic changes in particle energy. Solar wind particles were heated to millions of degrees as they passed through shock waves, while magnetic compressions increased particle densities by factors of 10 or more. Voyager had entered the chaotic frontier between the sun's influence and the deep interstellar medium.
These boundary regions were more than invisible borders. They were cosmic particle accelerators, where the gentle solar wind was transformed into high-energy plasma. They also acted as selective gates. Planetary magnetospheres blocked most solar wind particles while allowing cosmic rays from distant stars to break through. And the heliosphere kept out most interstellar particles while letting the solar wind stream outward into space. Each boundary represented a delicate balance between competing cosmic forces. Scientists soon realized that similar structures must surround every star in the galaxy. The Milky Way was filled with a vast network of unseen borders, shock fronts, plasma walls, magnetic barriers, all guiding and shaping the flow of charged particles across interstellar space. By understanding our own solar system's boundaries, Voyager had given us a glimpse into how stellar winds interact across the entire galaxy. And when Voyager 1 finally crossed the heliopause into interstellar space, it completed the first full map of our solar system's invisible architecture, from planetary magnetospheres to the ultimate edge of the sun's influence. But none of this would have been possible without one of Voyager's greatest breakthroughs: its magnetic field measurements, which overturned everything scientists thought they knew about planetary magnetism. The magnetic revelations. When Voyager began its grand tour, scientists believed planetary magnetic fields worked like Earth's, a simple dipole aligned with the rotation axis, generated by electric currents in a molten iron core. Voyager showed how wrong that assumption was. Jupiter, the first shock. Jupiter's magnetic field was the first surprise. Its magnetic axis was tilted 11 degrees, but more importantly, it was staggeringly complex and 20,000 times stronger than Earth's. Its magnetosphere was so enormous that, if visible, it would appear larger in our sky than the full moon. It was a magnetic giant beyond anything predicted. But Jupiter, for all its power, was just the beginning.
Uranus and Neptune, the impossible fields. Voyager's measurements at the ice giants revealed some of the strangest magnetic fields ever discovered. Uranus, magnetic axis tilted 59 degrees. Neptune, magnetic axis tilted 47 degrees. These were not small misalignments. These were radical tilts, unlike any planetary field ever observed. Even more shocking was that neither planet's magnetic field passed through its center. Instead, the magnetic dipoles were offset from the planetary cores. as if someone had buried giant lopsided magnets inside each world and left them floating off-center. This behavior broke every rule of classical planetary magnetism. It meant magnetic fields didn't always originate in planetary cores, and that interior structures of planets were far stranger than expected. Saturn, the magnetic perfection problem. Then came Saturn. If Jupiter was chaotic and the ice giants were distorted, Saturn was unnervingly perfect. Its magnetic field was aligned with its rotation axis to an accuracy that seemed physically impossible. According to theory, no natural magnetic dynamo should align itself so precisely without some external force keeping it in place. And yet, Saturn's field stood perfectly straight, a cosmic mystery that still challenges scientists today. Voyager's magnetic field measurements uncovered behaviors that no scientist had ever witnessed before. Jupiter's magnetic field, for instance, was constantly shifting as the planet's rapid 10-hour rotation dragged charged particles around in swirling, chaotic patterns. The entire magnetosphere rotated with the planet, creating a cosmic magnetic lighthouse, a rotating beam of charged particles sweeping across space like a giant celestial searchlight. Voyager revealed that magnetic fields were not isolated phenomena. They were deeply interconnected with the planets, their moons, and even their ring systems. Io's volcanic eruptions pumped sulfur and oxygen ions into Jupiter's magnetosphere, forming a massive torus of charged particles that reshaped the entire magnetic environment. Saturn's rings interacted with its magnetic field to produce mysterious spokes, features that gravity alone could not explain. Voyager also shocked scientists by showing that magnetic fields appeared in places no one expected. Ganymede generated its own magnetosphere, the first moon ever found with such a feature. Weak magnetic signatures were detected around certain asteroids and comets, suggesting that magnetism was far more widespread in the solar system than anyone had imagined. Temperature and particle readings confirmed that magnetic fields were architects of space environments. They trapped radiation, accelerated particles to near relativistic speeds, and forged invisible electrical circuits linking planets and moons through magnetic field lines. Magnetic fields weren't passive shields, they were active, powerful forces sculpting the space around them. Voyager's measurements dismantled the old, simple model of magnetic fields originating solely in planetary cores. Instead, planets appeared to host multiple magnetic dynamos operating at different depths and orientations. Planetary magnetism was clearly far more complicated and diverse than scientists had believed. These revelations extended far beyond our solar system. If Jupiter, Saturn, Uranus, and Neptune could each produce wildly different magnetic environments, then exoplanets orbiting distant stars might be just as diverse. Understanding magnetic fields became essential for assessing the habitability of alien worlds. The thermal universe, Voyager's infrared discoveries. While magnetic fields revealed the invisible skeleton of the solar system, Voyager's thermal measurements exposed some of the most extreme thermal environments in existence. Both spacecraft carried infrared detectors capable of measuring temperatures across landscapes more extreme than anything on Earth. From Io's volcanic hellscapes to the near absolute zero of interstellar space, Voyager mapped a universe where heat and cold stretched the limits of known physics.
The furnace moon. Io delivered the most dramatic thermal extremes. Voyager recorded volcanic hotspots reaching 3,000 degrees Fahrenheit, hot enough to vaporize metal, hotter than steel foundries on Earth. These weren't gentle lava flows. They were explosive fountains hurtling molten sulfur hundreds of miles into space. But just a few miles away, surface temperatures plunged to minus 260 degrees Fahrenheit, creating one of the steepest temperature gradients ever seen on a planetary body. Walking across Io would be like stepping from a blast furnace directly into a vat of liquid nitrogen. Europa, the cold ocean world. Europa presented a different mystery.
Despite being farther from the sun, its vast subsurface ocean remained liquid, hovering around minus 100 degrees Fahrenheit. Deadly cold for Earth life, but warm enough to sustain the largest known body of liquid water beyond Earth. Tidal heating from Jupiter provided just enough energy to keep this hidden ocean from turning to solid ice. Titan, the methane world. Saturn's moon Titan showed how a dense atmosphere could trap heat even in the outer solar system. Receiving only 1% of Earth's sunlight, Titan still maintained surface temperatures near minus 290 degrees Fahrenheit, warm enough for liquid methane to pool in lakes and rivers. Titan was the only world besides Earth with stable liquids on its surface, though made not of water but hydrocarbons. The ice giants, thermal paradoxes. Neptune and Uranus added new layers of thermal mystery. Despite Neptune being 30 times farther from the sun than Earth, its atmospheric temperature nearly matched Uranus. Neptune's powerful internal heat source overpowered the influence of sunlight, making distance from the sun almost irrelevant. Saturn's rings, cosmic heat engines. Voyager found that Saturn's rings also exhibited surprising temperature patterns. Some regions were warmer not because of sunlight, but because of particle collisions, electromagnetic heating, and tidal forces. The rings behaved like enormous, delicate heat engines powered by gravity and magnetism. Interstellar space, the ultimate cold. Upon entering interstellar space, Voyager measured temperatures near 4 degrees above absolute zero, minus 455 degrees Fahrenheit, the temperature of the cosmic microwave background. This was the natural cold of deep space, where almost everything except hydrogen and helium freezes solid. Yet even here, Voyager detected pockets of unexpected heat. Shockwaves from ancient supernova created plasma bubbles heated to millions of degrees. Despite their high temperatures, these regions were so thin that a physical thermometer would still read almost absolute zero. Magnetic heating across space. Magnetospheres across the solar system contained charged particles heated to millions of degrees by magnetic acceleration. Jupiter's radiation belts contained particles with effective temperatures hotter than the surface of the sun, even though they drifted within the cold vacuum of space. A universe of extremes. Voyager revealed a universe of thermal contrasts unimaginable on Earth. Within our own solar system, temperatures varied by more than 3,000 degrees, creating environments where matter existed in states impossible to reproduce in terrestrial laboratories. These findings reshaped how scientists understood energy flow, planetary evolution, and the potential for life under extreme conditions. And through it all, both Voyager spacecraft continued their lonely journey, nuclear hearts still glowing, carrying humanity's first messages into the interstellar dark.
Active volcanoes erupting on alien moons, global oceans hidden beneath frozen shells, hexagonal storms larger than Earth, twisted magnetic fields that defy physics, ring systems that sing with electromagnetic music. Every world Voyager visited shattered expectations. Each one revealed mysteries that forced scientists to rewrite textbooks and expand the limits of what seemed possible in planetary science. Perhaps Voyager's most profound discovery was this: our solar system is far more dynamic and alive than anyone ever imagined. Far from finding silent, dead worlds orbiting in darkness, Voyager uncovered a cosmic ecosystem humming with activity. Moons erupted with geysers, atmospheres howled with supersonic winds, magnetic fields created invisible highways, guiding charged particles across millions of miles. The outer planets weren't simply larger or colder versions of Earth, they were entirely different kinds of worlds, governed by their own internal rules. Voyager proved how far human curiosity can reach. Its instruments became our senses stretched across unimaginable distances, allowing us to see storms on Neptune, hear Jupiter's radio waves, and witness the violent birth of new landscapes on distant moons. These machines extended human consciousness itself, reaching into darkness where no biology could ever survive.
And each spacecraft carried something even more extraordinary: the Golden Record, a portrait of Earth encoded in music, images, and greetings, a message of hope for any intelligence that might someday discover these travelers drifting through the interstellar deep. Long after Earth forgets the missions that launched them, Voyager 1 and Voyager 2 will continue their lonely voyage between the stars. They will remain ambassadors of a species that once lived on a small blue world orbiting an ordinary sun. Their golden records will whisper across the cosmos with evidence that someone was here, that we existed, that we dreamed. Even now, the data streaming back from both spacecraft continues to reshape our understanding of the boundary between the solar system and the galaxy beyond. Voyager showed scientists how our star interacts with interstellar space, revealing processes that occur around every star in the Milky Way. One day, their nuclear hearts will fade. One by one, their instruments will fall silent. And yet they will continue onward, silent, eternal witnesses to the galaxy's unfolding. They will join the tiny fleet of human artifacts wandering the star fields, waiting for future beings, perhaps millions of years from now, to find them and learn that intelligence once blossomed here. The Voyager missions proved something timeless. The greatest discoveries are born from the courage to step into the unknown with open minds and precise instruments. By turning cameras and sensors toward the darkness beyond familiar worlds, we learned that the universe is stranger, more beautiful, and more alive than our boldest imaginations dared to believe. Both spacecraft now raced into the interstellar void, leaving the sun behind at speeds that will carry them past nearby stars over tens of thousands of years. They are humanity's first successful attempts to reach the infinite, transforming us from inhabitants of a single world into explorers of the cosmic ocean. The journey that began in 1977 has become a voyage that will outlast human civilization itself, carrying our message, our music, and our dreams into the star-filled darkness beyond the edge of everything we call home.